Zeros of a polynomial, day 2. So in the last video, we talked about the general shape of the polynomial. We really didn't get to the zeros of the polynomial at all. So in this video, we're going to focus on the zeros of the polynomial. So let's start with this first example. The example says graph the function f of x equals x times x subtract 3 times x plus 4. So in this function, we actually have 3 zeros. How do we find the zeros? The way we find the zeros is we would set the function equal to 0. So I can basically take x times x subtract 3 times x plus 4. And I can replace that f of x thing with 0. So this whole function becomes 0. So you set that equal to 0. The purpose of doing that, you're looking for the places where this graph will actually cross the x-axis. So all these places, the y value will be 0, starting at the origin and all along that y value is 0. So by placing that at 0, you can find the zeros. Now the next step is actually set the factors equal to 0. So set the factors equal to 0. And it's really nice they actually already have this factor. As we get better with this, it's less and less likely to give you the equation as a factor polynomial. But tonight, pretty much all the polynomials you have will be factored for you. So that's our first step. Set the factors equal to 0. My first factor is x. My next factor is x subtract 3. And the last factor is x plus 4. So I said x equal to 0, x subtract 3 equal to 0, x plus 4 equal to 0. So if that's the case, we have to solve each of these lower equations for x. This one is already solved for x. It says x equals 0. So that's one of my solutions. This one you can solve for x by adding 3. And you get x equals to 3. That's another 0. And the last 0 is, if I set this one equal to 0, I subtract 4. And I'll get x equals to a negative 4. So in this case, I have 3 zeros. The zeros are x equals 0, 3, and negative 4. A lot of times, this is represented as a set. So you may say a set of numbers, 0, 3, and negative 4. That'd be the set of zeros, and that symbol means set. And it looks better. This is like, oh, funny looking parentheses. But yeah, those are all the zeros. So I know the graph crosses the x-axis. I'm sorry, yeah, the x-axis at 0. It crosses at 3, so 1, 2, 3. And it crosses at negative 4, 1, 2, 3, 4. I know some other things about the general shape of this graph, considering our last night's video. If I can figure out the degree of this polynomial, I can understand whether the graph is linear, or is it quadratic, or is it cubic, or is it one of those functions that moves up and down several times. So, anyway, so you can find those things by actually finding out the general shape of that graph. But to know the general shape, our most important thing we need is our degree. So technically, you should foil all these things together, make it a bigger polynomial. But truthfully, you only care about the degree. So truthfully, you just need to figure out what would the highest value of x be. So you thought about this. X to this, well, these two binomials, 4 together to be x squared. I'll distribute this. Get x times x, which is x squared. X times positive 4, which will be a positive 4x. Negative 3 times x will be a negative 3x. Negative 3 times 4 will be negative 12. So, you can combine like terms here. So this is really x times x squared plus 1x, subtract 12. So these two binomials form together this trinomial. And this x, I can distribute it into the problem. So I distribute an x, I will get x to the third plus x times 1x is 1x squared. X times negative 12 is negative 12x. So that would be the polynomial written as before it was factored. So that's what the polynomial was in the beginning. So having that, I know some stuff about this polynomial. For one, I know the degree. So you should be saying right now what the degree is. The degree is 3. Now, how does that help us graph it? Well, by knowing that degree, I know how many turns it has. I know this graph has 2 turns. And if you remember from last night's video, the reason why it has 2 turns is the number of turns is always the degree subtract 1. So no, it has to change the. And what you may also remember is x cubed function, x to the 3rd power function, look like this. That's if x to the 3rd power has a positive leading coefficient. Positive leading coefficient. So again, we have a positive leading coefficient, it looks like that. You have a negative leading coefficient is turned backwards, where it would fall to the right and rise to the left. So if this is the case, it's also x cubed, but it has a negative leading coefficient. So we know this graph should look more like this because it's positive x cubed. And if that's the case, I know that I must go up and then come back down through this point and come back up again. And that's pretty much the graph. I mean, that's what the graph is. You could find other characteristics of it. Sometimes it can be really useful to find the y-intercept. We already knew the y-intercept in this case was 0 because it's where it crossed at. But that's pretty much it. That's how you graph that polynomial. I guess let's mention some other things too. For example, even and odd functions. All right, so since we have this graph up, we discuss whether or not it's an even or an odd function. It's an even function if it is symmetrical about the line y, well, the y-axis. That means that if I took this graph and I actually folded it to both ends, this end and that end, and brought them together, and you folded it down this line, the left side and the right side should actually lie on top of each other. If you folded it down, creased down this page, you wouldn't get that happening. It would not be symmetrical about the y-axis. So it's not even, because even functions are symmetrical about the y-axis. And odd functions are symmetrical about the line y equals x. So if you think about that, if it was an odd function, I should draw the line y equals x, y equals x. It's pretty much a line that wherever x is 1, y is 1. X is 2, y is 2. So pretty much a line that bisects the first quadrant and bisects the 3rd quadrant. So it's symmetrical about that line, it may be an even function. It's not even, it's an odd function, maybe an odd function. It's not, you're not sure unless it's also symmetrical about the line y equals negative x. So you draw the line y equals negative x. Also, and it's still symmetrical about that one as well, as in you folded a crease down the page and the graphs lie on top of each other on both sides of the line. It would be an odd function. This is not even or odd, it's neither. So even function. It's symmetric about the y-axis. What does it look like? It looks like this. All right, so this is a function. An even function will look like this. If you fold it down this line, this is y-axis, this side and the left side should lie on top of each other. A good way of telling is, let's say this is 3, and on the left side, it's negative 3. So look at the chance that may be an even function if you actually folded it down. You prove that. It could look other ways too, though. It could look like this. So you visualize, actually, this is actually perfectly drawn. You visualize folding this graph down, this axis. The side here and the side there should match. These two curves should lie on top of each other. If I was a little bit better and making sure it looked like it was even. Try to make it a little better. But this would be another example of an even function. So I folded it down this line. These numbers should lie on top of each other. this piece should lie on top of that piece. This curve lie on top of that curve. So that's pretty much what the even function looks like. Algebraically, even function is this. If f of x equals f of negative x, it is an even function. Basically what that means is this. Alright, so is the function f of x equals x squared plus 2 an even, odd, or neither? So it's an even function, odd function, neither. So the way you can find out is, you can make up a number for that. I'm going to make up a number. And we'll plug in opposite of that number. Let's say I'll plug in f of 3. If that's the case, it's going to be 3 squared plus 2, which is 9 plus 2, which is 11. So to see if it's even, I'll plug in f of negative 3. And still it's the exact same thing. If you plug in negative 3, it's negative 3 squared plus 2, which is also positive 9 plus 2, which gives you 11. So since f of 3 and f of negative 3 are equal to each other, are the exact same thing, both are 11, this is an even function. It would be an odd, well, I'll tell you about why how it could be an odd function. It's an odd function if one is symmetric about the line y equals x, the line y equals negative x. This is also said to be symmetric about the origin, so that would be the place right here. So if it's an odd function, it's symmetric about both of those. One of them is just a graph like y equals x to the third. It looks like this. It's kind of squiggly, but if you graph the line y equals x and the line y equals negative x, you would see that if you fold the graph down both of those simultaneously, or either one of those, you should see that they lie on top of each other. It should be an odd function. Algebraically means that f of negative x is saying that it's negative f of x, then it's an odd function, meaning this. So be sure to pause the video and write all these things down. But this means that if I plug in, say, negative 1 into this polynomial, I'll get negative 1 cubed subtract 20, which is negative 1 subtract 20, which is negative 21. So f of negative 1 equals negative 21. Now, if I plug in negative f of positive 1, means that I will plug in positive 1 to this function and get the opposite of it. So it's going to be negative 1 to the third subtract 20. So 1 to the third is 1. Subtract 20. So that 1 to the third looks like that. That's what it is. But it's going to give you negative, this is 19. So this is 20. So 20 isn't the same thing as negative 21. This is neither even or odd. Because if it was odd, they both have to be the exact same things. Same way, it's neither. All right, so multiplicity and the zeros of polynomial. Pause the video again, write down the screen. When you get done, understand this. You can look at this until this polynomial has 0 at negative 5, at 1, and at 4. But what's special about it is it goes through at these numbers, but it just barely touches it, or I might say bounces off the graph at this number. So because of that, you say this graph actually has 3 zeros. However, one of them occurs twice. Because it's a special case where it actually bounces off of it, that 0 actually occurred twice. And if you actually what the zeros were, you say the zeros are negative 5, positive 1, and 4. However, we know that the 4 has a multiplicity of 2. It actually occurred 2 times. Whenever it occurs at even number of times, it bounces off the axis. If it occurred an odd number of times, it goes through the axis. So the equation is y equals to x plus 5. Notice how the sign changed? Then the 1 becomes x subtract 1, and the 4 becomes x subtract 4 squared. And it's squared because it bounces off the axis. Good luck.